as usual, thank you for many of the previous speakers, and I have to admit that I'm jealous of Dan Iverson for being there at Silomar that I didn't. Anyway, thanks for the previous speakers, because every time it happens, they provide a very good introduction for my talk. Today, Ken Skidmore, John talked about QNMR, and so thank you for that. So what I want to talk about is a small tool that I have been playing around with related to craft, but it's a very small piece of information. So I'm actually going to talk a little bit about craft itself, and then talk about MISTA. So many of you have listened to my talk in the past. That would, I'm not sure if I can close this. I'm going to take it somewhere else. Okay. That is craft, old, new, real, and imaginary. So there are some stuff that you probably heard from me, stuff that I knew. There's some real stuff and some imaginary stuff that it's for you to figure out what it is. So with that, I want to first take up, I can't move my, for some reason. Okay. I want to talk a little bit about NMR 101. So here is a typical workflow that we all do, or we all trained to do in the past. So we take from FID, we do a Fourier transform, and then we do phase correction, baseline correction to whatever to our heart's content, and then that becomes the visual tool, because this is what we enjoy looking at. That is also the source of information, and we extract information out of it. Information, things like peak picking, maybe peak area, sometime line width, and so on and so forth. And that extraction maybe into a table or Excel spreadsheet, a notebook, and a paper napkin, whatever you want to call it. But in all the cases, the two ubiquitous unchallenged prerequisite, I always talk about this many times in the past, is the two events are phase correction and baseline correction. If they are so ubiquitous, they are considered part of post Fourier transform events. So let's say if you want to do a peak area or integration, something like that. Let us take a look at something like this. If you have a spectrum, something like this, if I can take my pen, okay. Oh, I can't use that. So that's not what I wanted, but it's okay. If you have a peak like this, and you have, you will do an integration, yeah? If you have something like this, you would say, okay, so I have peaks that are overlapping, so I'm going to do some kind of a deconvolution of the peak, whatever tool that I may have. This will also be probably into deconvolution type of methodology, because you have this C13 satellite of the DMSO coming too close to the peak. If you have something like this, it's a little bit more complex, so we will say, okay, I'm going to do a kind of a spectral matching or signal matching process. If you are interested in peak something like in between these two, a tiny peak like this, you may actually get into spiking experiment. You might actually spike with, if you know what that is, and you spike it and you generate area out of that, or try to come up with quantitation out of that. If you have something like this, immediately go and then do a CPMG experiment, and followed by conventional tools. If you have something like this, it's even more complicated. You are interested in these doublets that are sitting around, floating around there on top of these happens to be a blood serum. We actually may go into physical separation, some kind of a filtration experiment, a filtration followed by NMR, assuming the small molecules get through, the large molecules don't, and so on and so forth. The point here being, we use different strategies for different scenarios, which is okay. But in all of these, you also have the same thing. In all these strategies, you continue to have this phase correction, baseline correction. So in principle, QNMR strategy is dependent upon, this is QNMR strategy, meaning I am generating amplitude or integral or quantization, which is one of the properties of NMR. That strategy depends upon chemical shift separation, meaning frequency, big peak, little peak, meaning amplitude ratio, wide peak, sharp peak, meaning line width, in phase, out of phase, meaning phase. So in other words, amplitude, the strategy to generate amplitude information depends on frequency, amplitude, line width, phase, meaning one property of the NMR, measurement of that depends upon how the other four properties are in your NMR, in your spectrum. That is fundamental philosophical issue. So if we take, this is a slide, obviously, I steal a lot of slides from Frank. This is one of the slides I stole, a beautiful slide. A Fourier transform, you have a frequency, exponential decay, amplitude, phase, and noise. Fourier transform gives you frequency, Lorentzian line width, integral, phase, noise. It's the same thing. And the point being, the information content is exactly the same in both cases, whether you are in time domain or in frequency domain. It is how you extract that information is what changes. So if we look at this first slide again, our 1D process workflow, the key point in this slide is not about this workflow itself. The key point is we go from FID to spectrum to table, and that workflow dictates where the source of your information is. The source of the information is frequency domain, and we generate the whatever information that we are interested in. I just showed you an example of amplitude information or integral information. What if we turn that thing around? What if we take Fourier FID, we go to table, and then we go to spectrum instead of FID to spectrum to table? Because we just pointed out that FID and spectrum have exactly the same information content. They are just a Fourier transform counterpart. So if we can do this and you extract the information, and that becomes FID is a sum of several sinusoids, and your table is a sum of several exponential decay functions. And exponential decay functions has a frequency component, amplitude component, decay rate component, and phase. And we can sort of combine, filter, sort this into NMR related parameters. That's ppm, which is offset, amplitude, width, decay rate, phase. These are the four parameters that we are interested in. That's the table we are interested in. And we can generate a spectrum. What happened was, spectrum is not the source of information anymore. FID is a source of information. So spectrum becomes visual tool. And as a blasphemy, spectrum is actually optional in this scenario. If you don't need to see it, you don't have to see it. So you can always question, okay, fine, you just said time domain and frequency domain has the same parameter, same information. Yeah, you're going to build yet another processing tool. So it's going to be a skepticism right there. So let's just take a little bit about your pulse acquire experiment. We pulse. So let us say there are 3 magnetizations. They are all blue, green, and red. They are pointing in somewhere in space in the XY orthogonal Cartesian coordinate or laboratory frame of reference. They are pointing in the same direction. The amplitude is the magnetization at that point. But if you collect the data, they all decay. They decay and precess at different rates depending upon their frequency or decay rate and their frequency and decay rate. essentially, they process. So now you have this FID. The information at t equals 0 is the amplitude integral. The decay rate is rate of change of that amplitude with respect to time. Nothing to do with each other. One is amplitude at t equals 0. The other one is rate of change of that amplitude. So decay rate, which is the line width, should have no influence, or it should have nothing to do with amplitude if you measure it at t equals 0. If you happen to have a little bit of time after the pulse, you are to the phase, which is most of the time that's the case, because you have some hardware reason or some software reason, whatever that may be. They are all pointing in slightly different direction. That is your phase, and they all process the same way. Each one processes at their own speed. They process at their own speed, decays at their own speed, and we are collecting data at that time. So we have now 4 parameters: amplitude, which is a magnetization at time equals 0; decay rate, that's the amplitude, rate of change of amplitude; phase, angle with respect to that arbitrary coordinate at time equals 0; frequency is the rate of change of that phase. Again, all 4 parameters are independent of each other. So that's the advantage. We don't have to worry about one influence of one over the other. Phase correction becomes obsolete. We'll talk about that in a minute. There's one more thing that I used to talk about in the past. Quite a few people listen to it. This is, I call it a story of a singlet. So you have a singlet. Let's say you have a singlet. I look at this peak width, and peak chemical shift width. I said that's a singlet. If I were a conventional way of interpreting it, I want to quantify that. I look in my database and look for a reference signal. I find a reference signal that's 0.0005 ppm apart, and similar line width. I match the two. I match the height. I match the line width, and so on and so forth. The conventional way of doing it. I come up with 1.458. And if I am if I am a sloppy guy, I look at this and say, that's a out of phase signal. That's simply because the 2 frequencies are slightly different. So the subtraction of the 2 gives me some dispersive signal. I will walk away with this. But actually, that singlet is not a singlet. So the point, it is actually when you do a time domain analysis, it comes back and says, there are 2 models. One is at 6.022 ppm, and the amplitudes are 1:2, and so on and so forth. I know this is correct because this is a synthetic signal. Absolutely, you are going to say, oh yeah, you are cheating. You knew it and you are throwing it in. The point is not about whether this is right or that is right. The point is, in this process, we first made a definition that is a singlet. And then we said, I'm going to find a process which that singlet is going to fit to. That process can be anything, but I just happen to pick spectral matching routine. But that definition that it is a singlet was made because I looked at it, it looked like a singlet, it smelled like a singlet, it is a singlet. I made a decision that it is a singlet by purely visualization tool. And I said, everything within this line width ratio, I'm okay, that is perfectly acceptable. Whereas here, there is no such decision made. It came back and then said, there are 2, I can fit this into 2 models. And then as a scientist, as an NMR guy, as a synthetic chemist, I can say that is chlorine 37 to chlorine 35 isotope is really belongs to the same resonance or same molecule. I'm going to add them together. So the decision of that it is indeed a singlet is made after I know there are 2 peaks in there. So the logic is opposite. That's a fundamental difference. Now, over the period of time, I graduated. Krish, graduated from a singlet to a doublet, to a pair of doublet. Let's take a look at this one. Before I go to this one, let's take a look at here. Here, the 2 frequencies differ within the line width of the resonances. That's why they fall into it. That's why it looks like it's a singlet. Now let's take a look at a case of a doublet, a pair of doublets. This happens to be an interferogram of a toxic spectrum. There are two peaks in here, and at 150, they are separated by each one is actually a doublet. I'm giving you the answer. This is a doublet, that's a doublet. They have a J coupling of 16 hertz. So 1 over J is 62.5. If your T1 max is 33.6, that's 115 points. Our Fourier transform method, it says that I can separate these two. I am giving you two singlets. And if you have 256 points, it is still close, but not quite. It gives you almost a singlet. But we have several tricks in our Fourier transform tricks in our bag. I can do a 4 times linear prediction, and then I say, aha, I found this. I'm able to splice that out. I can get that doublet with 256 increments. That happens to be only 57 millisecond, much less than 1 over J. Except if you do this in time domain, that's the result you get. Because it's a fitting algorithm. It simply says the FID that you supply to me, even though this is only 33.6, I can best fit that to two doublets. And this with 33.6 millisecond, I don't even have to do any of these things. Game match point, I'm done. So there's a significant benefit to do these kind of analysis in time domain and try to decimate the data in time domain. So in other words, when I go from fit spectrum table to fit table spectrum, the parameters that define an NMR signal become independent parameters. They don't have dependency on each other. There is nothing called a phase and baseline correction. What is an error? What is there in terms of phase error? Phase is a phase. It is just error with respect to an absorptive peak. That's because we want it to be absorptive. So that's the advantage. So Kraft, up until now, I'm just explaining what Kraft is. Kraft is just that. It takes time domain to tabular domain. I'm not going to go into any of these details. These are all more or less automated, and so we can sort of focus our attention on how do I take this table of information and extract information that I am interested in. So if you are interested a lot more, there is a panel discussion coming up under IVEN umbrella on April 8th. Please, you can register for that. But today I'm going to talk about slightly different. I'm going to talk about MISTA. I'm not sure if I have the time. I'm only doing 18 minutes. I still have the time. So here is a reaction monitoring. This is courtesy Dave Russell. I should have put his name in that. So reaction monitoring, 60 megahertz. I have spoken about this in Panic. I have spoken about this in other places as well, where we have the product and the reactant that are right there. It's like a shoulder. This is not bad from a separation point of view. And then there is also a product right here with the reactant there. So yeah, we have done this. We have heard you. What is a big deal? So yeah, it's not a big deal. So you have a reaction monitoring, and you can strip this one out. Essentially, you can monitor that peak in the presence of all these guys. You can monitor this peak in the presence of all those guys. You can monitor the product here, reactant there, even this overlapped region. And interestingly enough, I can actually directly plot that in a kinetic fashion. That's my kinetic plots. I think Dave is going to probably talk about kinetic fitting to that, and how do you get a kinetic information out of that, and so on, so forth. I'm not going to talk about that. Dave will talk about that in the panel discussion. The point here being, it's not through the spectrum. They all came straight out of the spectrometer, which is output is a FID to spreadsheet, the information content. So spectrometer spreadsheet happens automatically. Everything else here is automatic. There's nothing in fact, it's the opposite. Everything in here is a visualization of the result. They are not the source of the result. Okay, so what? This is all we have heard this before. What's new? So I was challenged recently by one reaction that was sent to me. I can't disclose who this is. At least I didn't ask permission yet, so I can't. So here is a time course. Experiment. I am displaying two different regions, and so okay, what is the peak that we are interested in? We are interested in that two peaks. In here, I'm interested in this upfield region. I'm interested in this peak. I want to look at the time course of that peak. In the downfield region, I'm interested in the time course of that peak right there. Right, and this one is from my perspective, piece of cake. It's very well separated. You have the peak. You can actually see the peak right there. Even at the end of the reaction, I can do that. This one is challenging. So what happens is when you generate graph table, this guy, after about certain number of things, it cannot differentiate all the other junk right next to it in the presence of all these big peaks. It couldn't find a good probability of finding that peak. Visually also, it's difficult to say that. It says I can't give you any high probability. That's it. So it gives me 0. Whereas the other one was very good. So the problem here is I know I have it, but because of other issues like this huge peaks, again, I'm not going to go into the details of that. There's a huge high dynamic range problem. The residuals are incredible with respect to that. That's probably 10,000 to 1 in terms of dynamic range. So all these guys could never be modeled with any good probability in the presence of all these guys. So that's a problem that we are going to face. So how the hell am I going to solve this? Then it occurred to me, there is a normal procedure that we all do, at least people who are in trace analysis do, is what is called a spiking experiment. They have a sample of that compound. This happens to be, let us for an argument's sake, let's take this quartet as our trace peak. And I have a compound that I know, that's a reference compound I have. So that's my reference. I can spike it. I can spike that sample into my NMR tube, and then I can just spike it with a single amount, 1:1 ratio, or some ratio of 1. Or I can spike in some linear fashion, 1, 1.5, and then do any typical integration, peak height, whatever I do that. This is not something that I am bringing in new. This is, we all know this, spiking experiment, spiking to generate quantitative information of trace molecule, particularly in complex systems such as metabolomics or food sciences, is very well practiced, known procedure. But in my case, let's say I don't have the compound, I just have a reference table. That quartet might have come from, not from a pure compound, but a messy mixture, but I just know I have a graph table of that quartet. Then I could just add the table to my FID and then do a graph again. And so this is actually graph models, not a spiking experiment, meaning I'm not spiking the sample because this is not a reference sample, it is just a reference spectrum with that sample being there. It could be from one peak in a messy set of peaks. I'm just happen to find that peak in my reference sample. So I can add a model or set of models that belongs to that trace peak and then do this experiment. So if I do this, I can do these graph models. I can plot my amplitude of these graph models against each other with this spiking ratio. I get a beautiful straight line, and the intercept is the amplitude of the trace peak, and the slope is obviously the amplitude. Slope would be the concentration of this model that I added. But if I know the concentration, there are two problems here. If I know the concentration, I can calculate. The thing that immediately bothered me more than anything else was this R squared equals 1. This came out of Excel spreadsheet. R squared equals 1. To me, it just bothers the hell out of me because it's just too good to be true. But it's actually not 1, it's 99999 something. Then I say, okay, that I believe. Now, if you take the actual value, because this is a known set of model that I have, the expected concentration is 1.2 of this signal. The reference concentration from this signal is 8 millimolar. I know that, and I can calculate it. That calculated concentration is 1.197. So except I did not collect any number of data. I had collected this spectrum. I just have a model of that peak. So the moment I say that I just have a model of this quartet, which I know, and then I can add it to that, all models, adding any or all models is a fair game. I have a huge opportunity in front of me. Let's take, for example, this particular example that we talked about. Now, I don't even know what that peak is, those two peaks are, but I can do a graph of the first trace, which is the reactant, where the concentration of that signal is maximum. Amplitude of the signal is maximum. I don't know what it is, but I know it is maximum. And that's a graph model of the first trace of just that one peak. In the presence of all these models, I just have that one model. I can add that one model to all the traces if I want, as long as I know how much I added. I added one equivalent of that model. So if you look at the pinks traces here, that's 1:1 ratio of that model to every one of those traces added. And same thing here. Now, all the traces have that model or that signal either equal to the first trace or more than the first trace. So if you can do craft on the first trace, you can do craft on all the traces. Once you do that, I know exactly what I added, which is the first trace. I can take it out. And I can do this. So in general, this is a general principle, meaning that as long as you have a model that you have in your hand, you can in silico spike your FID at any ratio you want, any number of ratios you want, and do this analysis and generate the amplitude that you are interested in. If that happens to be a product, I will take the last trace, because product will be maximum in the last trace. It will be probably 0 on the first trace. I can take the product and then add it to all the traces and do this craft analysis on that. Again, you can now see that I can do crafting of this difficult peak as easy as this easy peak, just by simply taking the first trace, the model from the first trace, and add it to everybody. With that, I'm going to close. I just want to thank you for attending Ivan conference and stayed here to listen to my talk on a podium, whatever. So please come for the panel discussion on April 8th. And I want to thank Dan for many tools that he has built for me over the period. And of course, there is no miracle here. This is just looking at it from a different way. With that, I will close. Thank you.